Hello, my name is Ronan, and today I'll be teaching about mathematical induction and structural induction. And we're going to start with mathematical induction, and we're going to get right to it. So, mathematical induction is basically proving something by proving the base case is equal to 1, and then by proving that the function itself implies the next member of the function. So, what we start off with is in the summation of 1 to n of I equals n times n plus 1 over 2, where n is a member of the positive integers. So, first up, we have our inductive hypothesis, which basically we're just going to be rewriting what we already have, but it's a very integral part of the system. By that I mean that you're going to get points taken off if you don't include your inductive hypothesis in your mathematical induction. So as you can see, I just had let P of n equal to the equivalent to what we have up there. And that just kind of lets us do stuff with P of n and then use those changes to affect what we have right here. Alright, so next we have the base step, which is where we just plug in 1 to all of our variables for n, pretty much. So it's the summation of 1 to 1 of I equals 1 times 1 plus 1 over 2. And I'm just going to work that out really quick. It's, as you can probably guess, it's just going to be 1 equals 1 times 2 over 2, which is 1 is equal to 2 over 2, which is 1 is equal to 1, which is true. And so you use that to prove that, for 1, that the equation is true, because a lot of equations, if you throw in really small numbers, they can really mess up the equation. 1 especially for like divisions and stuff like that, 1 can really mess up your equations. And so by proving this, we're proving that it's also very helpful for recursive definitions, because if we have a base step is true, then we can work and use the base step for our recursive steps in order to figure out other parts of the equation. So now we're going to go to the inductive step, which is basically just the recursive step. And so the inductive step here is you're going to try and prove that P of k implies P of k plus 1. And we're doing this basically to prove that there are more members of this function that are true other than just 1. And this is basically our recursive definition. We're basically doing backwards recursion, where you start from the base step and go forward instead of starting from a given step and going backwards. So now we're just going to rewrite everything in terms of k. So I equals 1 to k of I equals k times k plus 1 over 2. You can see here. And then we're going to rewrite the summation out so that we can better understand what the step that we're going to do later and see what's actually happening to this summation. So the summation is basically just 1 plus 2 plus 3 plus ... because we don't want to write all these numbers out. We can't. Plus k equals k times k plus 1 over 2. And so now what we're going to do is we're going to add k plus 1 to each side of the equation. The reason we're doing this is so that we can try, because if we're adding something to both sides of the equation, it's like if we didn't do anything, and we're trying to get this right side over here in terms of k plus 1, which will look like, as a side note, since it's n times n plus 1 over 2, it'll look like n plus 1 times n plus 2 over 2. So that right there is what we're trying to end up with. and we got to work with this right here. So when you add k plus 1 to each side, you get 1 plus 2 plus 3 plus dot 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 plus k plus 1 equals k times k plus 1 over 2 plus k plus 1. So as you may be able to tell, the reason we wrote the summation out is so that we can add that onto the end of it and then change the summation to k plus 1 instead of just k. And as you can tell, we really haven't done anything to the right side. And that's because a lot of the really theoretical, hard to grasp things come from the summation aspect. Whereas with the right side, we're really just doing mathematical axioms. And so first off, what we're going to do is we're going to try and combine these two fractions. So we'll multiply 2 to the top and bottom of the k plus 1 off to this side. So that just gives you 2 times k plus 1 over 2. So now what we're going to do is we're going to combine the two fractions. And since we have two k plus 1s, we can have k plus 2 times k plus 1. Because of how the distributive property works, it'd just be k times k plus 1 plus 2 times k plus 1. Or what do we have here? K plus 2 times k plus 1 over 2. Obviously, we got that part. And as you can see, that is what we want. The terms are flipped, but it's multiplication, so it doesn't matter which order they're written in. And so then we go to our conclusion. And for mathematical induction, the conclusion step is probably the easiest, because you can just say k plus 2, k plus 1, plus 2, by mathematical induction. Yeah, all you really have to do is just rewrite your original formula and put it by mathematical induction. Yeah, you just want to write something like k, you want to write the summation thing. You want to have that little summation, and then have all that. And so that's mathematical induction. And structural induction is the exact same thing, just instead of with summations, you're using just numbers of elements of sets. So you would do 3n member of S, and in structural induction you use the recursive definition a little bit more. So inductive hypothesis, 2n equals to 3n member of S, and member of the positive integers. S is just a set, just some random set, doesn't matter what. Base step is basically that we're going to show that we're going to plug in 1. We're going to show that 3 of 1 is a member of S, 3 is a member of S. Sorry. Yeah, and in this case, S is equal to yeah, and so the base step is true here because 3 because of the recursive definition. Sorry about that. My phone was going off and I wasn't sure what it was. Very unprofessional, I know. And so after the base step, you go to the inductive step once again. And what you do in the inductive step is basically try and prove the next member of the set, or you want to prove basically that 3n implies 3 times n plus 1. So obviously we're going to prove p of k implies p of k plus 1. And so, you assume 3k is number of element of the set, because, sorry I haven't shown the paper off in a while. You want to show this a member of the set because, that's what we're trying to prove. And so, now what you can do is, since we know the base case is that 3 is element of the set, that we know that this is simply as that for the base case. And so what that means is that we can then combine step 2 and 1 together, 3k is number of s, and 3 is number of s, by combination with 1 and 2, or conjunction, not combination, say. And then the recursive definition, which I have written on another piece of paper, which is not written down here, very unprofessional, is that if x is a member of S and y is a member of S, that implies that x plus y is a member of S. And so we can then use that with 3. Okay, right there. So we can use that with 3 and get 4, which would be 3k plus 3 is a member of S. And since we know that, we can then do something with that mathematically to make it look like what we want it to. And what we do here is we factor out a 3 from each side. Not each side, but from each member. And we get 3 times k plus 1 is member of S, which coincidentally is exactly what we were trying to prove. Really easy. And then you have your conclusion, which is just p of n is equal to 3 and member of S by structural induction. Yeah, basically, structural induction is the exact same thing as mathematical induction, just you're using it to prove that you're just using it to prove that different formulas are true. And mathematical induction, you're using it a lot more for summations or inequalities, whereas with structural induction, you're using it to prove members of sets and stuff like that, structures, I guess. And that's pretty much it for me. If you have any questions, please feel free to email me at brogan@uga.edu. I know, awesome email. And yeah, that'll about do it. Thank you very much.